Hello guys, finally I came back with another video from series of a solution of partial differential equation numerically. In this video I'm going to solve heat transfer equation. So if you are interested, stay with me, and before that please don't forget to like and subscribe my channel. So let's start. This general form of heat equation, as you see, let me choose first this laser pointer, this one. Okay, this is the general form of heat transfer equation. Here in the U is representative of temperature, T is time, and X is coordinate. This coefficient D is diffusivity, and this function F, that is function of could be function of coordinate and time, is just heat source divided by C multiple to the rho. Here C is a heat capacity and rho is the density. So we should have initial condition at the zero time, at the starting of the time, and we assume that this is well defined with the function Jx, and our summation restricted to A and B, so X should be between A and B, and also we should have well-defined boundary condition, and we imagine that at the left boundary, and that we name it with A, it should be as a function like phi1, that's a function of T, and in the right boundary, that's localized at the point B, it should be some another function, well-known function that I defined with phi 2, and this is valid for when time is greater or equal than 0. I want to simplify this equation. Therefore, I imagine that the diffusivity is 0 and we don't have any heat source. Therefore, when I substitute this to value, I have this simplified equation. Left part is just first order with respect to the time, and the second part is partial differential equation with respect to second order partial differential equation with respect to the x. So I imagine that my left boundary located at 0 and right boundary, that is b, located at 1, and the initial function can be defined with some sine pi x. Therefore, this is our initial condition for x between a and b, and we imagine that at the left boundary the value of function is 0, and also in the right boundary this is also 0, and as we defined, a is 1 and b is a is 0 and b is 1. So as usual, if you look at my previous video, you know that in solution of a partial differential equation using finite difference, we should discretize our domain, and here we see the discretization a, b, and this is x coordinate, this is time coordinate, and here will represent the t, the value of t. That indeed here the u function is our temperature. So we assign j to the t-axis and we assign I to the x-axis. Using the definition of a finite difference method, can write this partial differential equation like this: ui and j plus 1 minus uij divided by delta t should be equal to ui minus 1j minus 2uij plus ui plus 1 and j divided by delta x squared. Here delta t is indeed our time step, and delta x here is our steps in space or in x direction. If I simplify this equation, just multiply both sides with delta t, we have like this, and by defining this meter delta t divided by delta x squared with s, we can have this simplified equation: uij plus 1 should be equal to s multiple to ui minus 1j plus 1 minus 2s uij plus s multiple to the ui plus 1j. So it says that if we want to find the value of function of u, that is in the temperature, in a previous time in a next time step that's represented with ij, represented with j plus 1, we should have the value of function at the previous time step. You see, all second subscribe is g. Here is g, here is g, and this one also is g. But the value of function at the x position should be at the grid I minus 1, I, and I plus 1. For imagine here is I and here is j. Imagine we want to find function at this point. So what we need, this is j plus 1, right? Because we go one step time further. So if we are interested to find the value of function here, what we need is only this 3 point. This one, that is ui minus 1j, this one, that is uij, and this one, that is ui plus 1j. In this solution, we don't need iteration. Maybe you can say why we don't need. This is very clear. And sometimes, if we want to find the value of function at this point, right, we need all neighboring value. This one, this one, this one, and this one. So if we need this point for calculation of value of function at this point, but this is unknown. So in this case, we have to define an initial guess, and we say that, okay, we imagine that this is our value of function in this point is something. Then we can find the value of function with this, and using iteration, we make this value of function at this point closer and closer. If you are interested to learn how this works, you can look my previous video that you can find the link exactly here. I just solved a Laplace equation in iteration, in an iterative method. At that solution, you need iteration, but because, as I mentioned here, you don't need iterative method, because all you need for calculation of value at the next time step related to the previous time step and different position. This is very simple. I think if you look to that video, it will be very clear for you. So I recommend to watch that if you didn't so. And the analytical solution of such a function with this boundary condition is easily can be find something sine pi x multiple to the exponential of minus pi squared multiple to the t. It is very easy, just calculate the derivative with respect to t and the second derivative with respect to the x, and you will see that both parts is identical. Okay, I think that's it for theory. So let's go to the MATLAB and start writing of code. Okay, how can I exit? Okay, I have MATLAB opened here, and also I wrote the code before, but I start writing again one more time with you. I define new script and start as usual. I start with CLC, clear, and close all. Okay. Oh, what we have, okay, I want to cheat a little because I wrote it here. Okay, what we need is the number of grid in x with in x equal, I just defined with very simple one. I define 3 for number of grid in x direction in a column, number of grid in t direction or in time direction is also 3. Okay, what else? We should define A, this is 0. We should define B, this is 1. What else? We should define T0. T0 is 0. We need final time, and I define it with TF. Let's define with 0.2. What else? Let me check a little. Okay, dx. Therefore, what we need is x in x direction, and this is nothing but e minus a divided by nx minus 1, right? And dt should be tf minus t0, not O. Oh, t0 divided by nt minus 1, right? What else we need? Okay, x should be changed from a with step ex to e column, and t should be changed as from t0 with the step of dt until tf, right? I think yes. And I think I defined everything. S. I defined the parameter S with, what was it? Del S is dt divided by dx squared. So where is it? This one, okay. And S parameter should be dt divided by dx squared. I don't put semicolon here because I need S the future. So let's start from analytical solution. Okay, analytical solution. So I defined analytical solution with capital UA, and let me assign a matrix for matrix UA, and this is zeros n. We say that, okay, I represent x direction and j represent time direction, so it should be nx and nt. Okay, let me just check, is everything okay? Yes, okay. So we should calculate this function in a loop for j from 1 to nt, right? It represents x y direction, yes. And again, another for sweeping in the x direction, I should change from 1 to nx. And what is our function? Another end. This is the function. This is UA of I and j. And what was it? This is sine pi x. Sine pi multiple to the x I, right? Multiple to the exponential of minus pi square minus pi square multiple to the p j, right? Okay, and here I define a figure and want to plot this analytical solution. So plot, not plot, contref of UA, capital A, UA, I think number of, okay, let me just check, sine pi x, okay. UA, this 200 represent the number of line, and color line should be none. The line color should be none. Okay, let me save this and editor file, save as this one, hit equation, direct calculation, second. This is the second code that I'm writing. Okay, 2, save, and let's run it and see is it work. Something is wrong. What is wrong? TF T0. Here is say that 0. It should be 0. 0 C. Okay. Index. What exceed from what? Index number of array elements 0, error in line 22. IJ should be equal to sine pi xi multiple to the minus p square. Everything should be correct. What's the wrong? Index exceed number of array. And x, I just defined 3, 3, 0, 1, 0, 0.2. dx is b minus a. Okay, and figure, not for figure. Okay, this is our analytical solution, and color map, I think. How was it? Color map. At 256 Check. Okay, what else? And I need color bar. Color bar 5, not color bar 5. Oh, color bar 5. And we have color bar here. Okay, did I define here maximum for color bar or not? Yes, and the color bar axis, let's define between 0 and 1. Control V, Control, okay. Okay, now this is our analytical solution. Let me define X label. X label should be X, and Y label should be E. Control C, Control V should be E. Let's check. Label, X label. I'm not good in writing, I think. Okay. E and X label, Y label, and title is Analytical Solution. Okay. 5. So we have analytical solution here. I just defined the number of grid only with 3, just 3 by 3 grid. I want to compare it with numerical solution. That's why if you want to write some coding, I recommend you to start with very simple case. It means that, for example, here you start but very small grid number, and the minimum one that I defined here is 3 by 3 because we have 1, 2, 3 grid and 1, 2, 3 grid. 2 of this grid should be devoted to the boundaries, right, left and right, and only the center grid should be calculated. So that's it for analytical. Let's define here calculator numerical solution. I define this numerical solution with capital UN, and this should be again zeros nx and nt. I just copy it from here, paste. Okay. What else? Okay, because I want to, we have two methods for solving of this this problem. We can either calculate it directly, or we can use the inverse matrix method. Also, I have also an example for inverse matrix technique that you can find in the channel. If you're interested, you can again use the inverse matrix technique. But implementation of this direct calculation is very easy in comparison to the inverse matrix. That's why I calculate it directly. So I just need it again. 4. I just do for loop, copy it from here. Control V. But here should not be analytical solution. Here what we have. Here it's ij plus 1. Okay. uij plus 1. uij plus 1. This is s multiple to the ua I minus 1 and j plus 1 minus 2 is 1 minus 2 multiple to the s multiple to the u a multiple ua ij plus, I think, yes, yeah, it should be plus, yeah, plus sui plus 1j plus s multiple to the ua, what else, I plus 1 j, not t. Also, I should put in minus 1 here, because when the maximum value for I is nx, here nx plus 1 appear that we don't have nx plus 1. The maximum is nx, so if we define here the maximum value for j with nx minus 1 and the maximum value for index in t with and 2 minus 1, it should works. What else? Nothing, I think. Okay, let's again plot it, and I just copy this command. Control C. Control V. Here should be. Oh, this should not be A. This is analytical, and numerical should be N. And capital N. And capital N, and we want capital N here, and this is numerical solution. What analytical? Oh, analytical solution, and this one should be numerical solution. I think everything is correct. Let's check. Not correct. Index in a position 1 is invalid. Index, yeah. Also here, look, we have index I minus 1, and when we start I from 1, here 0 appear. In MATLAB, we cannot assign 0 index for a matrix, and the minimum index that we can define is 1. So we should start this index from 2, 5. Okay, this is numerical solution, but terrifying. Why this is like this? Let me check one more time. Let me check it. Should be the same. UE. I divided minus 1 gen 1 minus 2s. I didn't define initial condition. Yeah, that's why this is 0. Now here that we define, okay, we say that our numerical solution is a 0 matrix that the dimension is nx by nt. So and we define that at the left and right boundary, our boundary condition, boundary values is 0. So it satisfied our boundary condition, but we forget to find the initial solution, initial condition here. Initial condition. And what is the initial condition? Just in a 2 and in 1 and 4 in 1 and 4 all. Okay, it should be sine I multiple to xi. This is our initial condition. Let me check. Just I disable this commands and run it again. And I want to see here where is command here. Open variable, I want to see UA. This is the analytical solution, and UN, numerical solution. Yes, you see here. So be careful, because here imagine that if you imagine this domain in MATLAB, it should be rotated 90 degree. I mean that here should be our initial function, should be somewhere here, right? But, and you see that in an analytical solution, the initial value is here, but it is it's localized wrong here. I think this one should be for first time, yeah, in this initial condition, right? So for the first j and all x should be like this. Let me run again and see the update. Why this is 0? It should not be 0. It should be 1, like this. 0, 1, 0. And this is indeed 0 because this is machine error. So why this is not 1? Strange. It should be 1 at the middle, because when x is 1, sine of when x is half, sine of pi over 2 should be 1. Let me check with previous code. Pi x. I should not put this here. So okay, let's work now. Sine of pi x. This is our initial condition at here, and this is our boundaries. Okay, this is just rotated 900 to the 900 to the right. So it should works now. Control T F5. Okay, this is numerical and this is analytical. You see, if you look at carefully, you think that they are differ a little, and we can see it from the value that we see here. This is analytical. You see the value is 0.3727, but here is 2. Here is 0.04, and here is 0.113. So let's calculate error to see how much our solution is exact error. And I defined it with just E, and this is nothing, but we want to see the absolute error. To A analytical minus U numerical, right? And I want to put it like this, so just Control C, Control V. I don't need this maximum limitation for color bar because the error should be less than 1, and we can see it easily. And error F5. Now this is error, and let's change the title error. Okay guys, you see this is error, and you see that error is 0.60. This is really high value, and like what as we see here, we have a great error. So why we have such a big error? This is very simple, because number of node that we defined for our domain is just 3 by 3 node. And we should have error, because if imagine that you have a polynomial function, and if you want to define this polynomial function with just 3 nodes, so it will be just 2 straight lines. So you cannot define this polynomial function with just 3 nodes. Therefore, in order to reduce the error, let's increase the number of grid. And I increased number step time 100, and I meant 10 times. And let's see, the error decreased. And if we compare, this is analytical, numerical, just compare it, we have again some error, and here, although maximum error decreased, but we have already it. So let's increase it 10 times and increase it 10 times again, I meant 10 for nx and 300 for nt, run it again. You see error decreased to 10 to minus 3. Maximum error is here, and this is 10 to minus 3. And if you compare, you see that numerical is very close to analytical, right? Analytical, numerical, analytical, numerical, and this is error. We can decrease error more by increasing it 2 times, 100, and this one 2 times. When we increase the number of grids, you see it's reduced to 10 to minus 4, and the error is less and less. So by increasing the number of grid here, you can easily decrease the error. Let me close this values. I want to show you something. Mathematically, you can. This is very easy that you show when S value. This is what is this? This is the ratio of dt divided by dx squared. When S value is greater than half, you will have divergence in numerical solution. Let me show you. For example, this is 600. Let me put it 100, and let me put it 50, and let's check the S. You see, S is greater than half. This is 4.8. You see how much is error? It means that we don't have a correct solution. 10 to power of 108. And if you see the numerical solution, you see analytical, numerical. We have completely divergence. So if you can prove it, this is very easy. But if you can't prove it, I can prove it in another video that the value of function S should be less than half. Let me make S close to the half. How? This is 50. This is 500. See, this is already greater than half, you see. So we should have big error again. So let me increase it 1000. This is slightly less than half. The S value is slightly less than half. We should have now accurate solution, you see. We have it. just what if I change it to 60? This is greater than half. I want to make it slightly greater than half and slightly greater less than half. You see, it diverge. So let's take 55. Just in order to be fast, let me disable all these commands. Control R and find the S value. Okay. Oh, I'm at 55. Again, 3. I just want to check the S to be slightly greater than half. 2, about 2. 1. You see, this is slightly greater than half. Let's see what's our numerical solution. I disable all this command with Control T and press F5 again. Let's see what will we have for. This is, I think, very small. So let me increase it a little. Control R. This is very close to the half. When the S function is half and greater than half, it should not work. But this is very close to the half. So let me just change this one with 1000 with 1, 2, 3. Maybe this one. I think it should not work. No, let 7. 980. No, yes, you see, this is just 0.01 greater than half, and let's see the solution. Control T, F5. You see a big error, not as big as the previous one, but we have the error is 3.5 here. And you see, this is the numerical solution, but with very huge errors at this point. You see? So, the conclusion in solution of a heat equation, this approach indeed is explicit solution. Why we say explicit solution? Because we see that the value of function at the next time step, that is represented with j plus 1, can be explicitly explained as a function at the previous time step, that is j. We call it as an explicit solution. We can have another solution, implicit solution. In the implicit solution, indeed, you should use another definition of this, the left part. I mean that if you wrote here uij minus 1 minus uij, this is also true according to the definition of a finite difference. That is known as implicit. In implicit, your S can be close to 1 and less than 1. At that point, also you will have a true solution. But when your solution is explicit, your S should not be exceed than half. As you see here, when it's slightly greater than half, we have a huge error. But when we decrease it by 1050, then it's less than half. As you see, we should have less error. And by increasing our number of grid and keeping the condition for S, that should be less than half, you can even decrease the error. For example, 2000. Before calculation, let me disable and Control R. I want to increase the number of grid. 100. S is large, so let me keep it at 8. Okay, 2500. Yes, you see this value for S is slightly less than half, and it should work. And error should be decreased. Control T, F5. Because number of grid is high, it should take a little more time. It's running. Okay, analytical, numerical, and error usually it decreases to 10 to minus 5, and if you increase the grid more, the error should be decreased more, but it will take more time. This is direct calculation. It is possible to solve this, as I mentioned, using the inverse matrix technique, but I solve it using that technique, and the error of inverse matrix is more than this method. Trust to me, I checked it, but if you are interested, please let me know in the comment. I can solve the same problem using inverse matrix, both explicit and implicit. I will show you that for when S is half and less than half, the explicit solution works well. But when it's greater than half, explicit solution doesn't work anymore. For implicit solution, when S is 1 and less than 1, it works again. But for higher than 1, it doesn't work. But the error of inverse matrix technique is more than what I show you here. I have it. Let me hit equation. Maybe this one is. Yeah, this is according to the inverse matrix. Let me just show you how much is error. This is for less number of grid. Okay, let me increase to, for example, 20 and 2000, 82,500. Exit. Okay, I think I should check this call. Okay, by the way, if you're interested, I can show you inverse matrix technique, but trust to me, the direct calculation error is less than inverse matrix. I think that's it for today. Please don't forget to like the video and share it with your friends, because I'm here to try to show you programming step by step, right? Because in solving our partial differential in coding, try to simplify the problem as much as possible. That's why I just start from very small number of grid and go step by step and check during the coding. I check to everything to be correct. That's it, guys. Thank you for your attention. Please let me know your feedback at the comment. I hope I post more video in the futures, although I didn't defend yet. I have defense at the end of this week, but after that I will try upload more video. Thank you and goodbye.